All right. Well, thank you so much, Sigve, for joining us at the end of your workday.
Yeah.
I know it's 5 p.m. in Norway right now, where it's 10 a.m. here in the central United States. So thank you so much for joining us, kind of at the tail end of your workday. But I am seeing your presentation mode, so you might want to switch
Okay. Let's
your
see.
screen. But yeah, I'm really pleased to have Sigve here. He's been working on a reporting engine to support the cancer community in and I guess you'll kind of introduce that portion of it. But I'm really glad to have you here. Sigve works for the Institute of Cancer Research in Oslo and focuses on cancer informatics. So thank you so much for being here. I still am seeing your slides in like the presenter mode. I'm sorry.
Let's how do I do this?
Sometimes there's like a switch screens or there's a or swap displays. Yes,
Like
that's perfect.
Okay, yep. Okay.
Great.
Okay, then we're good. Okay, I guess I can start.
Yep.
So thanks a lot for the invitation to present my work. So I'm Sigve, working at the Institute for Cancer Research in Oslo, Norway. I have also an affiliation to a center of excellence here in Oslo called CanCell, which is more basic cancer research. And I also have an affiliation to the Bioinformatics Center locally at the university. So today I want to present some work that I've been doing for many years, and that is sort of quite closely related to the work that you are discussing in these VICC meetings. So I have sort of developed two different tools or workflows to support precision cancer medicine or sort of tumor board work. So I'll spend most of my time talking about the Personal Cancer Genome Reporter, or PCGR, which is sort of focusing on the somatic aberrations that we find in the tumor. I will talk a bit about the project that we are doing with the French group on how we can use molecular findings in the tumor to find clinical trial opportunities. This is also an ongoing project that we are working on. In the last part of my talk, I will sort of mention the sister workflow of PCGR, which is called CPSR, or the Cancer Predisposition Sequencing Reporter. So this is not looking at the somatic aberrations, but more the what's happening in the germline. So it's a slightly different tool and a slightly different sort of classification scheme. So as many of you probably are aware of, there are a lot of interpretation solutions available. And they are typically web-based. So you have the cancer genome interpreter from Barcelona, and then you have the molecular oncology almanac in Boston, and the molecular tumor board portal, which is now hosted by SciLife Lab in Stockholm. So we, of course, would argue that standalone sort of non-web solution could represent a good alternative, in that you can feed such an interpretation tool into your sort of standard bioinformatics pipelines. And we think this can also sort of cater more for high throughput processing of samples. And what has also been important for us in Norway is that using sort of non-web solutions is kind of critical because we do all of our work in secure environments where we don't really have access to the internet. So we need to sort of have some solution that works without access to that. So PCGR and CPSR, they are essentially tools that aims to harvest a number of precision therapy measures from high-throughput sequencing data of cancer patients, both the tumor and the germline profile of the patient. So both of the tools are sort of standalone. You can run them on your own computer if you like. They are open source, and we only rely upon publicly available reference data. So everything is free, and no sort of licensing is really needed. So the tools, they work in a way so that you report everything on a sort of per case basis. So when you run the tool, you feed them with a sort of single case. So let's say a VCF file from a single patient, and a list of copy number aberrations, and then the tool, which is sort of installed inside this conduct framework, which is a way to install all the software dependencies of the tools. That is sort of querying the external knowledge resources or the reference data, which in turn is giving you the sort of final interpretation report in HTML. And we also provide other types of output. We also have made the tools sort of available as sort of containerized so that people can run them on systems that require this, so both Docker and Singularity. This is something that many users have sort of asked for. So one thing that is important to convey is that these tools, they are interpretation tools, and they're not the sort of tools that will call or that will identify variants in the tumor. So this has to take place upstream of PCGR and CPSR. So what you should really sort of have in place before you run these tools is a sort of set of high quality variants. And I would also like to say that the sort of quality control of the variants is not really a focus of the tools. So we really expect that users have done a quite solid job with that on that sort of part before they run the tools. So with respect to the input data for PCGR, so right now it accepts primarily point mutations and copy number aberrations. We hope to expand this in the future with also structural variation. We are also working on supporting RNA fusions, which is also something that people have asked for support. In addition to these actual mutation data, we want the users to specify what type of tumor that they are looking at, because this we need in order to classify variants according to actionability. So this is a sort of a really simple input where we essentially want the users to sort of give the basic or a primary tumor site of the sample that they are looking at. And in the release we are trying to push now, the users can also feed in expression data or RNA-seq from the same tumor. So this is somewhat of a preliminary work, but this is something that we think also will be useful to show in the approach. So one thing that we spend quite a lot of time on is to sort of harmonize reference data or prior knowledge. So a lot of the sort of questions that these tools want to address requires a fair amount of sort of data integration and harmonization. And you can think of this both to be sort of at the variant level and also at the level of genes. So if you think of the variant level, you typically want to know what type of consequence the different variants have that you feed into the tool. Has it been seen previously? Was that seen in the germline or somatically? And if it was seen somatically, in what tumor types was the variant seen, and so forth. And you would be interested in whether a variant is likely giving a loss of function to the gene, or whether it's more likely gain of function occurring in hotspots or in functional domains and so forth. And probably most importantly, we want to know whether the variants are actually actionable or whether they are actually markers for drug sensitivity or drug resistance. And at the level of genes, we sort of want to know whether genes are cancer relevant, whether they are known to be predisposing cancer genes, whether they have known tumor suppressive roles or oncogenic roles, and so forth, or whether they are known targets for cancer drugs, either sort of known approved targets or those that are currently in development. So for this, we use a fair amount of existing resources, both sort of data and also software, to try to answer these questions. We sort of stick by far to openly available resources. So for the actionability data, we use only VICC and the data from CGI, since both of these are sort of freely available resources. So as I mentioned, in order to sort of make all these data readily available for processing, we need to sort of harmonize them and integrate them. And this is a major part of the work of developing these tools. So I think the sort of the most rapidly evolving knowledge is probably the biomarkers themselves, and also the types of drugs that are available and what they are sort of approved for and indicated for. And we really appreciate that some initiatives, such as the one by VICC, has been erected to facilitate such integration. But we also see that it's not maintained, or at least the knowledge base integration is not maintained up to date as far as we understood. So what we do for PCGR and CPSR is that we have sort of made a lot of sort of supporting data packages that allows us to sort of update the reference data that are used by the tools. So we have like a sort of a suite of tools. So one is for sort of phenotype ontologies that are sort of strictly focusing on the oncology domain. And then we have one package which sort of looks at cancer gene annotation, so sort of integrates information about what kind of role different genes have with respect to tumors. So tumor suppressor annotations, oncogene annotations, predisposition genes, and so forth. And then we have a dedicated package where we have tried to sort of make a classification of targeted drugs, specifically cancer drugs. And also here we also harmonize biomarkers from VICC and CGI so that they are sort of integrated. So all of these are freely available, so you can check them out on my GitHub page. So this is something that we have spent quite some time on to make work properly. So the key functionality of PCGR is to prioritize the variants we see in tumor according to guidelines or published recommendations. So in the version we are trying to release now, we do this sort of along two different axes. So the first one is the oncogenicity, which was sort of published with VICC in 2022. And then the second axis is sort of prioritizes the variance according to actionability, which is based on the ACMG and EMT guidelines. So PCGR is also trying to do a lot of other things. So things I won't go into detail here, but I think the message I want to convey is that the tool is more than a variant interpretation tool. It also tries to harvest a lot of other measures that can inform upon precision treatment. So it reports upon mutational signatures. It classifies the tumor with respect to microsatellite instability. We report the mutational burden, which is important for as an indicator for immunotherapy questions. And we are starting to address RNA expression analysis. So far we have sort of developed some functionality where you can find tumor samples that are sort of similar to yours, basically looking at the correlation of the expression. We also try to find sort of expression outliers by comparing the expression of your sample against the sort of reference cohort. And we show sort of the immune contexture by using one of these RNA deconvolution tools. The PCGR gives you as output a configurable, interactive, and transparent report so that the users can sort of look at the results and interact with the data. We also support assays where you have only sequenced the tumor, so we do some internal filtering. And we also provide, of course, standard support for assays where you have done tumor control variant calling. And we support also both of the most recent builds of the Human Genome Assembly. So a lot of people apparently are still stuck with build 37, and that is where you need to make support also for that. So the first prioritization technique that I sort of want to showcase is the oncogenicity prioritization. So here we essentially PCGR has sort of implemented the operating procedures that was published by ClinGen and CGC and VICC. So it kind of gives me, I think it will give you kind of an idea of the choices that one has to make when you actually want to implement guidelines in a tool. So these are kind of the how the sort of guidelines are laid out. So you have different properties of the variants listed here, and then we have sort of points towards the benign scale if it carries these properties, and points towards the oncogenic sort of side if it carries these properties. So what we have done in PCGR is that we have sort of picked up all the recommendations in the papers, and we use GNOMAD, and we use sort of cancerhotspots.org, and we use also all of these in silico predictions to provide computational evidence. And we also use other information from PCGR, such as tumor suppressor annotation and ROS subfunction to give evidence to these criteria. So what we don't have in PCGR, and what I think is important to convey, is that this part, the functional data of the proposed operating procedure, we don't really have that readily available. So this criteria sort of indicates that there should be evidence from well-established functional studies showing oncogenic, non-oncogenic effects. And I think to my knowledge, most of these data are found in sort of curated resources that are frequently licensed. So for now, we don't have support for that. So in our current implementation, with this information lacking, we see that sort of the scores are kind of shifted somewhat to the thresholds that were was proposed in the guidelines. So this means that in our implementation, we have sort of shifted the threshold somewhat for the oncogenic, oncogenic variants. So this is essentially a screenshot of the report where you can sort of interact based on the sequencing depth that you see in the tumor and the control sample and the allelic fraction of the variants. And then you can also go in and look at the classification that was done according to oncogenicity. So when you click here on each variant, you will then see what kind of criteria that kicked in to make this variant oncogenic. So as the sort of second axis of prioritization, we do a sort of actionability classification. So there are not only guidelines proposed by the ACMG and AMP, but also the ESMO scale from the European side. But what we have sort of realized is that we think it's easier to implement the American guidelines simply because they sort of fit better to the data that is found within the clinical actionability databases. So this is why we have so far only concentrated on the ACMG and AMP guidelines. So how this is working is that we essentially try to find aberrations in the tumor that are also located in these actionability databases. And if we see that there is strong evidence for clinical impact in VICC or CGI, and this occurs in the same tumor type as the tumor type of the query, then we place these variants in tier 1. And then if we find strong evidence in a different tumor type in these databases, or weak evidence in the same tumor type, we put them into tier 2 and so on. So this is kind of how it works in PCGR. So one thing that I sort of would like also to convey is that the whole process of matching variants in the tumor towards biomarker records in these databases is not that straightforward, because you have biomarkers, they can sort of occur at different resolutions. So by far, most of the biomarkers are sort of very accurate. So they occur at the sort of exact amino acid or genomic position level. But you can also have sort of a lot of biomarkers so you can have them at the codon level, you can have them at the exon level, particular consequence types in particular exons, and you can even have sort of type of mutations that carries an oncogenic effect. So PCGR tries to sort of address all of these kinds of settings when it finds biomarkers in the tumor sample. So just want to show you here, right, how this is shown in the report. So we kind of make a note of this to the user that you can have matches between variants in the tumor towards known biomarkers at the sort of exact genomic position amino acid and codon level, and then you can have matches between entries in your tumor sample with sort of more loosely defined biomarkers in biomarker database. So here we're looking at variants in tier 2, where we see that 4 different variants in the tumor sample are matched with sort of more loosely defined biomarkers. So the first one here is a APC loss of function variant, and here PCGR sort of finds that this type of alteration in the tumor fits with an APC loss of function biomarker. And so similar here, the biomarker is TP53 loss of function, and then PCGR sort of portrays this also as a hit. So of course, these biomarkers are of course less, I would expect sort of less reliable than the ones that are sort of more exactly positioned, but at least the tool is also then able to sort of expand a bit more upon the findings in the tool. So I want to show you also some sort of screenshots of what's sort of found in the final report. So initially, we provide the users with an overview of sort of the tumor site, the purity and quality, if this is provided, which is not the case here. What kind of assay has been performed, and also the target size of the coding genes. And then the sort of tool gives you some statistics of the variant types that are found. And then you can also look at sort of the distribution of the variants with respect to allelic fraction. So you can sort of see where at what sort of frequency these variants are found in the tumor. And we also sort of portray them sort of along the genome and also show some statistics. So this is the first part is sort of merely to give an overview of what's found in the tumor. And then we go on to show all the likely oncogenic and oncogenic variants. So you can sort of interact with all the variants that was found and different annotations of that, both the coding variants and the non-coding variants. And then we also provide the actionability data. So here we see in tier 1, we see one particular variant that was sort of exactly matched against at the sort of exact amino acid change. And then we have one sort of more sort of loosely defined biomarker. In a similar fashion, we have support for copy number aberration, where you can look at the actionability of copy number events. And so here, in this case, we see sort of known actionable events is CDKN2A, which is frequently lost in different tumors. And we also see sort of different gains of genes that were found in the segments that was provided by the user. So the sort of limit to what is considered to be a gain is something that the user can sort of configure, in a sense. And you can also then sort of figure out whether these comes from sort of broad copy number events or whether they come from sort of very focal type of events. So as I mentioned, we also provide an analysis of mutational signatures. So this gives you sort of an idea of the types of sort of processes that have shaped the tumor. So this is actually a case where the analysis gave a sort of suboptimal fit of such signatures. But so some part of the tool you can sort of see suboptimal analysis, and then you sort of need to configure the tool and run it once again. For MSI, we also do a sort of MSI prediction. So this is a classifier that we have developed based on TCGA. So we essentially basically look at the sort of distribution of indels and the load of indels, whether you have mutations in MMR genes in a way that enables us to separate the MSI high tumors to the MSI or MSS tumors. So it performs quite well on exome and whole genome sequence data, but we haven't really made this work for panel type of assays. So one project that I also like to sort of mention that we are working on is how to find clinical trial opportunities. So this is, I think, is an important endeavor that such tools should also address, and is something that a lot of commercial companies are trying to support. I think most of them are not sort of looking at the molecular data, but more the sort of clinical data of the patients. So the challenge here is that data in these clinical trial registries are still very much unstructured and not really suited for computational processing. So in one sense, it means that it's kind of semi-structured, meaning that you have the trials are listed with sort of defined fields, such as what are sort of the drugs or interventions that we are going to test in this trial, and for what tumor type or conditions. But still, it's kind of limited in their use of ontologies or control vocabularies, which is very useful when you do bioinformatics. And then you have sort of text within these clinical trial descriptions that are completely unstructured, so completely free text. So typically, this is where the molecular information is listed. So you can have an inclusion criteria for a particular trial that says that the patient should have documented EGFR mutation, for instance, exon 19 deletion, exon 21, and so forth. So this is kind of the challenge to pull out that information efficiently. So we have sort of we are doing this together with a group in France, in Bordeaux. So we're doing sort of using two different approaches. The approach that I've been working on is a very simple one, where we essentially just devise some patterns or some regular expressions that we are applying on the eligibility criteria of the clinical trials. So essentially looking for gene symbols and sort of dimensions of particular mutations. This gives us very simple and interpretable results, but this is of course very much limited by how sort of sophisticated you can write these rules. So here is sort of a regular expression where we try to sort of convey how gene inactivation are listed in clinical trials. You also need to sort of cater for the fact that people create a lot of spelling errors in clinical trials, so you sort of have to have some level of fuzziness to the rules. So the alternative approach that the French group is working on is to sort of learn these the way that these rules are written more comprehensively through kind of LLM type of techniques. And this will sort of result in a dedicated algorithm called trial match AI, so that we are working on. But the simple approach that I've been working on takes essentially data from clinicaltrials.gov and tries to do sort of entity recognition of drugs and the conditions, the sort of different cancer types, and then a bit more sort of sophisticated recognition of sort of the actual aberrations that we see in the eligibility criteria. So from our sort of initial sort of exploration of the results, we see that in clinical trials, we see that there are sort of a few genes that sort of are listed quite frequently. So the EGFR and BRAF and ERBB2 in breast cancer is a very frequent sort of molecular marker that is listed. And we also see that a lot of the trials sort of list sort of wild type as some sort of eligibility criteria. So this is kind of what we have seen so far. And we also see that some tumor types are much more enriched with molecular markers used in their eligibility criteria than others. So lung and breast is by far the sort of the tumor types with most data on this. And what we sort of find, I guess, most intriguing is that approximately 1 out of 3 molecular markers mentioned in these clinical trials, they are of the type sort of gene mutation or gene positive negative. So this is, of course, makes it quite difficult when you have a patient with a set of aberrations to understand whether your patient will sort of fit the eligibility criteria for a given trial. So it could be that whether a gene is positive or negative, that there are some sort of implicit information in that motion. So finally, I want to sort of also mention that we have a workflow that is completely focusing on the germline side of things. So this is called CPSR, Cancer Predisposition Sequencing Reporter. So this is a slightly different ballgame than the somatic case, because there are specific guidelines for germline events. And why is this important? Well, it is important to find these variants in cancer patients, because it allows us to implement surveillance, not only for the patients themselves, but also for family members. You can also do risk-reducing interventions. It may impact surgery, and it also can have actually impact on targeted therapy. So this was published in 2021 in the International Journal of Cancer. So the first thing that CPSR allows the users to do is to sort of design the set of genes that you want to report upon. So here you can either sort of choose from predefined sort of cancer gene panels. So here we use panels sort of readily available from the Genomics England panel app. So you can choose from different sort of cancer syndromes or sort of tumor susceptibility genes. Or you can sort of design your own sort of virtual gene panel based on a sort of large compendium of genes that is implicated with cancer predisposition. And the way we do classification in CPSR is that we are largely inspired by another paper which came out in 2017, but was not sort of made publicly available. So CPSR sort of implements more than 30 of these classification criteria that was sort of outlined in this Sherlock paper. So it kind of works in the same way as the oncogenicity sort of guidelines, in the sense that you get sort of points towards the benign scale, and you get points towards the pathogenic scale, and then you aggregate all the points, and then you get sort of a final pathogenicity score. So we have sort of calibrated thresholds in CPSR against known classified variants in ClinVar, and it works fairly okay. There are, of course, these borderline cases where you have almost a similar amount of pathogenic cases and also variants of uncertain significance, but in the reporting from CPSR, we make this sort of, we highlight this to the users that you should pay close attention to those variants that are sort of difficult to classify. So some of the things that we are still working on is to integrate things that we are reporting on somatically with the things that we're reporting on in the germline. And we also realized that a lot of the curation that the curators do here locally at the hospital, they are very much interested in cases where you have sort of combinations of biomarkers in the patients and what kind of impact that may have. And as far as I know, there is not a lot of information on that in these actionability databases, but this is something that I think will be important moving forward. I also mentioned that we want to support RNA fusion events. So this is something we are doing in collaboration with FIM in Finland. So this is ongoing. The same also with, they want to integrate drug profiling data. This is also something that FIM is collaborating with us on. So they essentially have they harvest cells from the tumor, and then they do in vitro drug profiling, and then they essentially want to provide this also within the same report as PCGR, so that you can see what kind of drugs that responded in vitro to the tumor cells. And I think in the future, I think if we can sort of feed in a bit more sophisticated input from the tumor and the patients. So right now, we only have a very simple information about the tumor, so only the primary site. So I think if we can sort of enrich that information towards what is sort of known in the reference databases, I think that sort of interpretation would be a bit more nuanced than it is today. And one thing that we are challenged somewhat by is where we also have a number of pediatric cases at the hospital. But in these cases, the reference data that we typically use for sort of late onset cancers will not make a lot of sense. So we're struggling somewhat to find relevant reference data when it comes to the analysis of pediatric tumors. So if anyone has a good overview of that, we are very happy to get input. So finally, just want to acknowledge all my collaborators, so particularly the team in Oslo. So Hege Rustnes, Oslo University, these are the PIs of the national precision medicine efforts in Norway, and have been very central in sort of pushing precision medicine in Norway. So I'm very closely collaborating with a group in Melbourne with the development of PCGR and CPCR, particularly Peter Diakonis, who has been instrumental in all this work. We're working with a group in Bordeaux on the tri-matching, and with the group in Finn on the expansion of PCGR with RNA fusion and in vitro drug screening data. And also want to acknowledge Cancer, which is providing funding for this effort. And also want to sort of convey that a lot of the stuff that was presented here will be sort of shortly out in the release that is coming this month. So with that, I'm sort of happy to take questions.
Thanks so much for this wonderful talk. I'm taking over from Beth here. This presentation really touches base with a lot of topics dear to my heart. So I'm really impressed on what you're doing. And I have a few questions on what you presented, but I would like to also open the floor first to the audience if you have any questions. Maybe while you're thinking, let me start with one on the harmonization of evidence levels. I might have missed that, but you seem to be able to integrate evidence levels from different databases, so semantic information. How exactly are you doing that? And how are you working with conflicting evidence levels here?
So I think we're not, I mean, I'm basically relying on Civic and this resource from Barcelona, CGI. So currently we are essentially, we are harmonizing them in the sense that they we sort of transform one to the other so that they are sort of kind of semantically similar, but we don't really. So if we see the similar type of evidence in one resource and the other, we don't really merge them. We list them as separate entities. So there are bound to be duplicate information as we have it now. So we don't really sort of merge them. So it's a semi.
Okay, so it's. Yeah, so it would be similar to CBio portal, where you basically have evidence from OncoKB and Civic listed separately.
Exactly, because yeah, it is quite challenging to understand whether an entity listed in CIVIC is in fact the same evidence that is listed in a different database. So this is why we don't really dare to merge them yet. But I mean, I would be happy to, if there was like the stuff that VICC did some years ago, where they tried to sort of harmonize the different knowledge bases. I think that's a tremendously useful, at least for the tools I'm developing, would have eased bottleneck like that.
Yeah, I mean, one could think of, because it's usually based on evidences from publications, what one could think of using here, in this case, large language models to summarize the text from the different evidences, and then maybe use that as a basis for normalizing.
Exactly.
Might be a bit far-fetched, but but it's I think that would be a good use of large language models in that respect, in my opinion.
I agree. I'm sort of I'm starting to pick up on how powerful they are for doing a lot of things. So I think you have a very good point.
Yeah, and then on using those large language models, I mean, really, you could almost adapt like a civic model of curation there too, where the large language model picks something up, and then you have like a crowdsourced check of approval afterwards or something. It would be really interesting model.
Yeah, but I mean, you have to be aware of the challenges. Then, if we think of what we did with the large language models, as soon as you get in very rare entities and rare variants, you're just bound to pick up hallucinations, and then it's getting complicated. So, but I think text summarization and then like showing similarity between text might be an option. So if you're interested, that's something I would love to chat later in more detail, because that's maybe a bit too far for this discussion.
Yeah, but that's, I would be interested. It sounds like a fun project.
Yeah. I do have another project on the clinical trial matching, though. And to the other people in the audience, you feel free to also add your question in the chat. But while you do so, for the clinical trial matching, I mean, you have two approaches for that, but all of them are based on clinicaltrials.gov. From a clinician's or patient's perspective, this is kind of missing information, or whether or not the clinical trial is still open and whether it's in the area. Do you have any ideas on how to include that type of information?
Yeah, I mean, clinicaltrials.gov. I mean, we have also worked with ECRIN in Europe, which has a large repository of European trials. But I think the data that they provided us, I think 95% was already on clinicaltrials.gov. I mean, you have in clinical trials, you have location information, so you could apply like a simple filter initially, zoom in on the sort of geographical location, and then also maybe zoom in on the tumor type, and then make some recommendations for which trials are mostly relevant. So what we have sort of from the data that we have looked at so far with our collaborators in France is that some of the tumor types are largely matched by sort of non-molecular features, so clinical properties of the patients, and not so much the sort of molecular events, which we think is really exciting. But we have to sort of admit that so far, I think the sort of what can I say, the treatment history, the sort of performance status of all of these properties that are listed in the eligibility criteria are, I think, more useful right now than all the molecular information.
Yeah, but I have the impression that updating on availability of trials or arms is really then still a job to follow up in person and on site, and this seems to be quite time consuming as far as I know. I mean, that's nothing you can solve with the big databases, because I think it's really here up to keeping that kind of information maintained.
Yeah.
I was just wondering whether you have any ideas on maybe including local data on trials and also on.
No, we don't really. We mostly have been sort of playing with clinicaltrials.gov and sort of trying to make sense of that so far. But I think you have I think there could be sort of pieces of information that we are missing that might not be available explicitly on clinicaltrials.gov.
Yeah, but that might be the benefit of your on-site and local approach, that you could actually feed in additional, maybe even sensitive data. I really like that about PCGR.
Yeah, that's true.
Right. Are there any other questions from the audience? Beth, do you have any?
Yeah, so if somebody wants to check out the GitHub and your information, they have some feedback for you, is there a mechanism for that, or would you just like people to email you with any feedback?
Yeah, I mean, I guess my talk will be posted on YouTube, and there are links, there are email. So I tend to sort of keep all my stuff on GitHub. So if you want to reach out and post issues or whatever, feel free. I'm happy to get any feedback.
That sounds great. And then I wanted to ask another question about kind of like how you deal with licensure changes, like all of your data repositories that sit on the back end are publicly available. What happens when they become licensed? Because I know we've seen that happen with a couple of resources on VICC harmonization site.
This is something that I find really challenging, because a lot of people here locally, I mean, they essentially want all the information that is out there, whether it's an OncoKB or Civic, they don't care. They want everything. And I am sort of saying that I cannot ship my piece of software with OncoKB, because that's essentially violating the licensing.
Yeah.
What I could do is to more sort of create maybe plugins so that people, if they have a licensed piece of data, then they can use the tool still to sort of enable people who has access to those resources. But it's but I kind of tend to like that the stuff that comes with these tools should be free.
Right. Yeah.
It's kind of been my policy.
Yeah,
that makes a lot of sense. Go ahead.
Can that would be, I just want to have a follow-up question on that one.
Yeah.
How modular is your tool right now? Would you be able to integrate another like local database? Because I assume that every molecular tumor board somehow collects evidences for their patients and has some kind of forms, databases.
Yeah, I would like to say that yes, it's very modular and you can do it very easily. But I will have to sort of think a bit. But we try to sort of improve that part all the time to so that you can expand the reference data sets. but that's not at the top of my head. I mean, I would have to actually be faced with a data set in order for me to say how easy it is.
Yeah, definitely. Okay, thanks so much for taking the time and presenting and for this great overview. And I think there are a lot of good ideas on how to continue, and I could continue discussing with you for quite some time. So,
Thank you so much.
Very happy to, for the invitation to be able to talk. So happy.
Great. Well, thank you so much for sharing with us and sharing all the great things that you're doing over there, and for being so open and transparent with your process as well. So I really appreciate it. All right. Well, have a good evening.
Yeah.
And
And have a great day.
See you all soon. Yep.
See you.